In this last example, we are going to take a look at the limit. Here is our function. We have a rational with an absolute value in the denominator, and we're going to be focusing on the limit as x approaches 1. So we're going to take a look at the left side and the right side, see if they line up. And I have no idea. We need to create ourselves a visual. We're going to do it by hand. So first thing that I do notice, though, is that x cannot equal 1. Right? Causes 0 in the denominator. That's a problem. So we're going to do a little bit of math because I do need to figure out how to sketch this thing, and it's kind of a hot mess right now. And so let's see what it looks like. So let's start with factoring. So I'm going to factor out a 2, and that's going to leave us with x squared minus a 3x plus a 2 divided by this absolute value of x minus 1. And then we're going to factor that further, where we're going to have two things that multiply to 2 that add up to -3. So x minus 2 and x minus 1 multiply to +2, add up to -3. There's our factors. All right. And then we still have an x minus 1, the absolute value of it. So here's the thing about the absolute value, is that it's very situational whether you actually need it to apply the absolute value or not. And so if I have, if I plug a 10 in, 10 minus 1 is 9, the absolute value is really not needed, so we wouldn't apply it. But if you plugged in a -10, -10 minus 1 is -11, the absolute value would change the sign and turn it into a positive. So there's kind of a threshold of where that is needed and when it is not needed. So when x is greater than 1, like 2 minus 1, you really don't need the absolute value. So if it is greater than 1, the function that we're looking at is, we have our top that's factored, and the bottom really doesn't need the absolute value. So I can really just leave it as an x minus 1, but then those are going to undo each other. So really this thing nicely simplifies out to 2 and x minus 2. Right, but then when does the absolute value actually kick in? And that's when your x's are less than 1. So if you were to plug in 0, 0 minus 1 is -1. The absolute value is needed to change the sign. So what does it do? Well, let's rewrite our function here. Okay, and then we still have this x minus 1, except that x minus 1, whatever that value, we need to change its sign because anything less than 1 would create a negative. And so then another negative would cancel it out. So the x minus 1 still cancels, but we now have a negative that we can apply. So this piece is going to look like -2 times x minus 2. So what we have going on is a piecewise. We have situations. All right, so let's take that information, let's take our two equations, let's take our constraints to it, and let's figure out what this equation looks like. We can graph it, and then we can do our limits. All right, so when x is greater than 1, and then when x is less than 1. All right, and I had to kick out 1 because it causes a denominator, a domain issue. Cause the denominator to be 0. So if I look at the x minus 1, right, here's our equation, but I'm going to distribute the -2 in to kind of make it, it's going to be a linear, be easier if I had it not in factored form. So -2x plus 4, I distribute the negative in, and then if I distribute the negative here, you got a 2x minus 4. Okay, so there's our piecewise. Let's see what the graph of this thing looks like. All right, so if I graph the top one, it's one that the graph kind of shifts from this linear that's going down to this linear that's going up. Let's see if they line up. Let's see if there's a hole in there, a break in the graph. Don't know. So this one, we're going to start at y-intercept of 4. We're going to go down 2/1. So y-intercept of 4 down 2/1. And I'm going to end with a hole. And so this section is looking like this. And then this part of the graph doesn't really kick in until 1, but I need a y-intercept at 4. 1, 2, 3, 4. And then I'm going to go go up 2 over 1, and here's where it's going to kick in, and then up 2 over 1. And then we go 2 over 1 again and again and again. All right, so there's what our graph looks like. Once we have our graph, now we can look at all the pieces. Give some more space. So the limit as x approaches 1 from the left, and it's pretty common for us to look at the limit where we have a domain issue. So a lot of times, most graphs don't have problems until you have a domain issue, and then you have potential breaks in the graphs, or you have holes. So we really kind of want to analyze and see what it does. So let's take a look. As x approaches 1 from the left, which is here, we would be approaching a y value of 2. And then if we look at x approaches 1 from the right, if we're approaching it from the right, we're approaching this y value of -2. And since they don't line up, then our overall limit as x approaches 2 does not exist. So that's an example of that kind of a situation happening. So it happens probably more often than not. At worst case, you have a hole, but you can have an asymptote, you can have a break in the graph, you can have lots of different things. So those are just kind of a couple different scenarios. One last example that we have is visuals right now. Eventually we'll talk about how we algebraically do some of this stuff. But right now we have a visual, and we're looking at the limit as cosine 1 over x as we're approaching 0. So if you were to graph this, Desmos would be an amazing way to graph this, because you can really zoom in, is the closer you get to 0. So if we're approaching it from the right, this graph doesn't focus on a value. It oscillates, right? And so here's what a table of this looks like. If we're approaching 0 from the right, we're getting infinitely close to 0. Our y values are not like focusing in on one value like they did on this table, where if we were approaching from the right, we were getting closer and closer and closer to a specific value, right? So this table is kind of showing us that we're not approaching a specific value. This graph is oscillating and getting more, the oscillation is getting crazier the closer we get to 0. So for this, our limit as x approaches 0, like there's no way that this thing focuses on a value, and we would need to really look at both sides. But if they're just asking that and I look at one side and it goes crazy and it oscillates, then I don't have a limit. So the cosine of 1 over x does not exist, right? And it's because as x approaches 0, the graph is oscillating. Okay, so that is a little bit of an introduction to very much a visual introduction to doing your limits. But the biggest piece of this is, in order for an overall limit to exist, then the left and the right sides have to equal the same thing. All right, and then we'll talk about more algebraic ways to do this.